We will discuss different types of probability. First, what is probability? Probability is the likelihood of an event occurring. All probabilities exist on a scale from 0 to 100%. 0% likely to happen is something that is impossible. It cannot occur. 100% likely is something that is definitely going to happen 100% of the time. An even chance is considered something that is 50% likely to occur. Anything less than 50% but greater than 0 is considered unlikely to occur, and greater than 50 but less than 100 is considered likely to occur. Describe the likelihood of the probability of selecting a tie-dye marble from the bag as impossible, unlikely, equally likely, likely, or certain. Before we answer this question, as just a quick side note, recall that the way that we write probability questions often is with a capital P and then in parentheses the event that you're trying to determine the probability of occurring. Since there are 4 swirly tie-dye marbles in the bag, out of 10, that is a 40% chance of happening, which is unlikely because it's less than 50%. From a standard deck, a card is selected. Describe the likelihood of P red, the probability of selecting red, as impossible, unlikely, equally likely, likely, or certain. Half of the deck is red and the other half of the cards is black, so that is 50% likely to pick red as long as it is a full deck of cards, so that is equally likely. The bag contains 10 marbles. Describe the likelihood of P red or green as impossible, unlikely, equally likely, likely, or certain. There are 4 greens and 2 reds, which makes for a total of 6 out of 10, which is likely to pick a red or a green. When discussing basic probabilities, usually we are looking at what is called theoretical probability. This is a prediction of the likelihood of an event occurring based on your knowledge of the event. So for example, the likelihood of you rolling a die and landing on a 2 is 1 out of 6 because there is 1 2 on the die and 6 total sides. Experimental probability is when you actually conduct a trial or experiment and you record how many times something occurred out of the total number of times you performed the trials. Let's take a look at some examples of the 2 different types of basic simple probability. On the left-hand side, what is the theoretical probability that if I spun that spinner, I would land on an odd number? Since there are 8 spaces and half of them are odd, that would be a 50% chance of landing on an odd number. However, on the right-hand side, we have what's called a frequency table. The first column shows the outcome, all of the 8 possibilities of what I can land on this same spinner here on the left. I can land on a 1, 2, 3, 4, 5, 6, 7, or 8. And the frequency tells me how many times I actually landed on each of those numbers. So first we need to figure out how many total times did I spin the spinner by adding up all of the numbers in the frequency column. And then I'm going to tally up how many of them were odd numbers by adding up how many times I landed on the odd numbers on the spinner. When I do that, I get a total of 17 odd numbers out of 40 total spins. Let's take a look at a couple other examples. These are not in your notes, so you can pause and give these examples a try, finding the probability and then determining if that would be experimental or theoretical probability. You rolled a number cube, find the probability that you rolled a 5. There are 3 5s rolled out of a total of 29 rolls, so that is 3 out of 29, which is experimental. A probability experiment has 4 possible outcomes, A, B, C, and D. Outcome A is 4 times as likely as each of the remaining options, B, C, and D. What is the probability of outcome C occurring? If A is 4 times likely, and if we consider all of the other ones as being 1, that is a total of 7 possible outcomes, because that would mean there will be 4 A's and 1 of each of B, C, and D. So there's 7 total possible outcomes, 1 of which is C. That's 1 out of 7. This would be theoretical because we haven't actually done it, and it doesn't necessarily have to occur that way. One last thing we need to discuss when discussing simple probability is what a complement is. And a complement is all of the outcomes that are not in the event itself. So for example, if you roll a number cube and we want to calculate the probability that you would land on a 5, we know that is 1 out of 6. The complement of that is everything that you roll on a number cube that is not a 5. So that would be 5 options that aren't 5s out of 6. And the way you can determine if something is a complement to the event is if you add them together and you get all 6 out of 6 or 100% of the possible outcomes. Now that we've looked at simple probability, let's talk about compound probability. To do that, let's try this example first. How many different possible combinations of results are there if you flip a coin 3 times? And what are they? Pause and take a minute to try to answer this question. You can do this by drawing a tree diagram that would look something like this. Our first flip has 2 outcomes, heads or tails. Our second flip also has 2 outcomes, but depending on what I flipped first, that's a different combination. So if I landed on heads first and heads second, that's 1 pair. But if I landed on heads first and tails second, that's a different combination. If I landed on tails first and then heads, that's another set. And then tails and tails is another completely different possible outcome. Finally, our third flip adds a third branch to the tree, which shows that if I landed on heads first, heads second, and heads third, that is 1 possible outcome of all 3 flips. Heads first, heads second, but tails third, that's a second completely different possibility. Heads, tails, then heads, that's our third possible outcome, and heads, tails, tails is our fourth. We repeat similarly with tails being our first flip, and then we can see that there are a total of 8 possible outcomes in our tree diagram. Maybe a slightly easier way to list these is by making just a list of all the possible outcomes. And you can abbreviate here like I did: heads, 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 tails, heads, tails, heads, heads, tails, tails, etc. The trouble with making a list is it can be easy to forget if you've already tried something or missed something. So you have to be very careful when making a list, especially if you imagine if the number of possibilities is way bigger than 2 heads or tails, this list can get really long really fast. So when that is the case, when we have way too many possible outcomes to list or draw a tree diagram for, then we can recognize that there is a simpler way to calculate the total possible outcomes, which is by multiplying the total possible outcomes for each event. For example, if I have my first flip, I know I have 2 outcomes possible, heads or tails. On my second flip, I know I have 2 outcomes, heads or tails. And for my third flip, I know I also have 2 outcomes, heads or tails. To find the total possible outcomes, a lot of people think we would simply add those together, but it is actually that we multiply them together to get 8, as we saw in our tree diagram and in our list. This is called the fundamental counting principle, which just states that you multiply the total possible outcomes for each event. Let's try a couple examples of problems similar to that. You're playing Yahtzee, a game that requires you to roll 5 dice. How many possible outcomes are there? There are 6 total possible outcomes on each die, so 6 times 6 times 6 times 6 times 6 is 7,776 possible outcomes. A common mistake, again, is taking 6 sides on a die and multiplying that by 5 because there's 5 of them, which gives us only 30 possible outcomes. But remember, die number 1 itself already has 6 possible outcomes. So I could land on a 1 on die number 1, and then on die 2, I could land on a 1 again, and on die 3, I could land on a 1, die 4, I could land on a 1, die 5, I could land on a 1. If I repeat that with keeping everything the same except changing the last one to landing on a 2, and then again changing the last one to a 3, a 4, a 5, and a 6, that's already 6 possible outcomes with only changing one of the 5 die. So you can see that 30 is not nearly enough to account for all of these die needing to show all the possible outcomes. Example number 2 says you create a passcode for your phone. The passcode can be up to 6 digits long and includes numbers 0 through 9. How many total possible passcode combinations exist? Including 0, there are 10 digits, 0 through 9. If there are 6 digits in your passcode, that's 10 6 times, or 10 times 10 times 10 times 10 times 10 times 10, which is 1 million possible outcomes. These are also the same as doing 6 to the 5th power and 10 to the 6th power. Consider that you are going to pick 3 cards from a standard deck. How many possible outcomes exist? Pause and give this a try. You may have come up with one of 2 possible answers. Maybe you said that there are 52 cards in the deck, so that's 52 times 52 times 52. But maybe you considered, what if I don't put that first card back and I end up with 52 times 51 times 50? You can see that the total number of possible outcomes is different depending on whether you replace that item or not. First, let's discuss what are we doing here. We are looking at compound events, the likelihood of 2 or more events occurring. When we have 2 or more events occurring, there are 2 different types of compound events that occur. We have what are called independent events and dependent events. Our independent events are where the outcome of the first event does not at all affect the outcome of the second. Things like flipping a coin and then rolling a die, or even rolling multiple die, or rolling 1 die 3 times. Just because I land on a 1 the first time doesn't mean I can't also land on a 1 the second time. The other example would be picking a card or a marble, but also replacing that and putting it back. Dependent is where the outcome of the first event will affect the outcome of the second. For example, picking a card from a deck and not replacing it, because now there are fewer cards in the deck to pick from. This occurs in games like any card game where you have people picking cards from the deck and holding them in their hand, or Scrabble where you're picking letters out of the bag and putting them on the board. To find our compound probabilities, just like we did with finding the total possible outcomes, we're going to multiply them, but instead of just talking about the total possible outcomes, we're going to multiply the specific probabilities together. So for example, if you and your sister are playing a game, she needs to roll a 6 for each of their next 3 turns to win the game. What's the probability that she would specifically roll that 6 3 times in a row? So the probability of rolling a 6 on a die is 1 out of 6. 3 times in a row is 1/6 times 1/6 times 1/6. Which is 1 out of a 216 chance that that will occur, 3 6s in a row. If you're drawing a marble from this bag that has 20 marbles and one is picked and then replaced, what is your probability of picking green, and then green again. So green has a 5 out of 20 chance of being picked. For the first pick, we pick it out, we put it back. We are also assuming when we do this that the one that I picked the first time was green. We don't know if that's going to happen. This is theoretical, but we're assuming it's green. So we have a 5 out of 20 chance of picking green the first time. I take it out, but then I put it back. And then that means that there are still 5 greens in the bag and still 20 marbles. So I have a 5 out of 20 chance. I'm going to simplify these just to make it easier to calculate without having to simplify large numbers at the end. So you have a 1 out of 16 chance of getting 2 greens in a row. Now let's consider that same example, but not replacing the first green after I take it out. So again, we had a 5 out of 20 chance of picking that first green, but now it's gone and I don't put it back. So there are only 4 greens left, and there are only 19 total marbles in the bag altogether. So that gives me actually a slightly higher chance of getting that marble the second time around. Typically, we simplify our answers when we are writing probability. Now that I'm saying this, I'm just thinking, we had 1 out of 16 chance. Now it's 1 out of 19. That's actually a less chance of happening because I picked green and I took one of them away. If it was a different color that wasn't green, then it would make my chance of picking green the second time increase. But since the first one I picked was green, that will lower the chance of picking a green slightly. But you can see how not replacing it changes the problem. In this case, because green was picked first, I have 1 less green and I also have 1 less total. If I had picked green first and then we were asking for, say, blue the second time, the total number of blues, being 6, doesn't change, but the total number of marbles would still reduce to 19. A common misconception is, like, if I have 5 greens, that I'm taking all 5 out, but I'm only picking 1 marble at a time. We only say there's a 5 out of 20 chance of picking green because that's how many there are, but we're not taking all of them out. So if I was doing green then blue instead of green and green, the number of blues stays the same, but the total reduces by 1. Here are a few extras for you to try if you'd like. Pause if you want to try them.